Hey everyone, and welcome back to the AI Research Roundup. I'm your host Alex, and today we're diving into a really interesting paper called REPA-E, Unlocking VAE for End-to-End Tuning with Latent Diffusion Transformers. So the big question here is, can you train a latent diffusion model and its VAE tokenizer together, end-to-end? Usually that doesn't work well, but this paper shows it can be done effectively using something called representation alignment loss, or REPA loss. And the results look pretty impressive, significantly speeding up training and even improving the final image generation quality. So figure 1 here really helps visualize this. On the left, you see the traditional way. The VAE is frozen, and only the main diffusion model, here shown as SIT blocks, gets updated by the diffusion loss. Then there's the naive approach, where you try to update both with the diffusion loss, which, well, doesn't work well. And then we have REPA-E, their method. You can see the alignment loss is used to update the VAE, while the diffusion loss, with a stop gradient, updates the SIT blocks. The graph on the right hammers home the result. REPA-E, shown in blue, reaches a much lower FID score way faster than the other methods, showing that huge speed up, like 17 to 45 times faster. Building on that speed up, we saw this next part shows how REPA-E actually improves the VAE itself. The visualizations here using PCA show changes in the latent space structure. For one type of VAE, the SDVAE, it helps learn a smoother, less noisy representation. For another, the NVAE, which was a bit over-smooth, it learns a more detailed structure, and the chart confirms the performance benefit we saw earlier. REPA-E gets much lower GFID scores compared to the baseline REPA for both these VAE architectures tested here. So building on how REPA-E improves the VAE, Figure 3 really digs into why this representation alignment approach works so well. You can see again in the PCA visualizations on the left, using the REPA loss for end-to-end tuning maintains useful structure, unlike just using the diffusion loss, which kind of washes things out. The key insight here is shown in the middle plot. There's a really strong correlation between this representation alignment score, called CKNNA, and the actual generation quality, the GFID. Higher alignment means better images. And finally, the graph on the right shows that REPA-E, in green, pushes this alignment score higher and faster than standard REPA, explaining its performance boost. So table 1 here really gives us some hard numbers on why that naive end-to-end approach with diffusion loss is problematic. It measures spatial variance and total variation in the VAE's latent space under different training settings. You can see that standard training, or using the REPA loss for end-to-end tuning, keeps the spatial variance around 17 or 18. But look what happens when you try using the diffusion loss for end-to-end. The spatial variance crashes down to 0.02, and total variation plummets from over 6,000 to just under 90. This confirms that diffusion loss collapses the latent space, making it too simple, which hurts the final images. Okay, so we just saw how the naive end-to-end approach messes up the latent space. Figure 4 here gives us a nice visual comparison, showing the actual image quality differences between standard REPA and their REPA-E method over training. You can see rows of generated images, eagles, dogs, cats, squirrels, at 50,000, 100,000, and 400,000 training steps. It's pretty clear the REPA-E images, on the bottom rows, look much more coherent and higher quality, especially early on. Even at 50K steps, they seem better formed, and by 400K steps, the improvement is really noticeable. This really shows that end-to-end tuning with REPA-E translates to better pictures, faster. So we saw how REPA-E leads to better images faster during training compared to standard REPA. And figure 5 here really showcases the final quality you can get with this method. These are images generated on ImageNet using their end-to-end tuned VAE and the SIT-XL model. Just look at the variety in detail, from the eagle's feathers to the texture on the strawberries and the sharpness of the shark. It really demonstrates the high-quality generations that REPA-E enables at the end of the day. So we just saw those really nice final images from the SIT-XL model using REPA-E. Table 3 here gives us the numbers to back that up, and shows it works across different model sizes too. It compares standard REPA training with REPA-E for SIT models, base, large, and XL. Looking at the generation quality metrics like GFID and SFID, lower is better, and inception score, where higher is better, REPA-E wins consistently. For example, with the XL model, GFID drops significantly from 19.4 down to 12.8. So yeah, this confirms REPA-E provides substantial improvements no matter the scale of the diffusion model. Okay, so those numbers really drive home the point. REPA-E gives consistent gains across the board. Well, to wrap things up, this REPA-E method seems really promising. It effectively unlocks the VAE for stable end-to-end tuning with diffusion transformers, which we saw leads to better image quality much faster. This is important because it opens up new possibilities for improving these powerful generative models. That's all for this episode of the AI Research Roundup. Thanks for tuning in. I'm your host, Alex.